Hi everyone, my name is Wenqi. Today I'm going to present our KDD 2025 paper called PipeRAG, which is a work that addresses the system efficiency aspect of retrieval-augmented generation. First, let me give a quick recap of RAG or retrieval-augmented generation. And the key idea here is to pair large language models with retrievals from knowledge databases. So in this example, the user asks a question about Thomas Edison's invention. Now, instead of letting the model generating an answer directly, the question is firstly used to retrieve knowledge from a database. This can be private data and can also be public data such as Google or Bing's entire internet collection. So in this example, in response to this query, the retrieval procedure may find documents highlighting Thomas Edison's contributions, and then these documents are included into the prompt so the model can generate a more well-informed response. However, sometimes one retrieval might not be enough because sometimes the user questions are more complex than a very straightforward question, like tell me Thomas Edison's invention. So we may actually need to break down the question into multiple steps, like a chain of thought process. And in this reasoning process, there can be multiple questions generated along the way, and they require different sources of documents to be retrieved. So in this case, we may actually need iterative retrievals along the way of the generation process. So people use these large reasoning models today. At the time we conducted this research back in 2023, there was another model called Retro, which was invented by Google DeepMind, and that was the first work to introduce this iterative retrievals. But the concept is very similar. For example, here we have two stages. You can see on the left-hand side of this figure, we have the retrieved content. On the right hand of this paper figure, we have this generated content. And here, during the generation process, let's say generating the first 64 tokens, I'll use this latest 64 tokens as a query to retrieve some content. So let's say we use C1 as the query and retrieve the content R1. And after that, when generating the second chunk, I'm going to use the retrieved content from the first chunk. So we're going to do this cross attention between C2 and R1. And R1 here essentially is encoded by a shallow encoder model into Kiwi cache. And we do this so on and so forth. So for C2, we're going to invoke another retrieval and retrieve content R2. So for the generation of C3, I'm going to refer to this latest retrieve information R2. So in terms of algorithm perspective, this is fine. We do iterative retrieval and we get always updated retrieve content. On the other hand, from the search perspective, we find that retrieval can be actually very expensive. So according to this latest paper we published at ISCA, which is a top computer architecture venue, we found this very large scale retrieval, such as Google or Bing scale, can be even more expensive than the generation itself. So that leads to a lot of performance overhead. And even worse, we have all these retrievals multiple times along the generation process. So here in this figure, you can find this timeline. On top of this, we can find the inference timeline. And on the bottom, we can see this retrieval timeline. So you can find these dependencies between inference and retrieval. So we do inference C1 and we retrieve R1. And before we can handle this retrieval, we cannot start generating the second chunk of C2. So there's a strict dependency, and because of this inference and retrieval are typically running on different hardware, this means either type of this hardware is going to be idle at any time of the point. So it's a huge system inefficiency issue here. So in this work, we propose PipeRAG, which basically aims to improve the system efficiency for this very popular RAG paradigm with their iterative retrievals. So now let's further define the goal in terms of efficiency, because whenever we optimize ML workloads, they're always two-dimensional. One is the quality, another is the performance. So in terms of quality, we want to optimize metrics like perplexity, QA accuracy, etc. And from the system perspective, we want to optimize latency, which means how long the user have to wait before they see the result. And also throughput means how many requests the system can handle at any given moment. But let's take a look at what we do with the algorithm side. So from the algorithm side, we already see this efficiency because of the idleness. So we borrow one very common concept from the system perspective, which is pipeline parallelism, which basically says that we want to overlap the execution of latency of generation and also retrieval. However, it's not very straightforward to do that because, again, we have this dependency between retrieval and generation. So as you can see on the top right of this figure, when we generate the chunk C3, we actually need the retrieved content R2. So what we do here is that we allow some prefetching of this data, means that we can fetch the data with a stale query window. So we allow some staleness of this retrieved content. So as you can see here on the bottom side of this figure, to generate chunk C4, we only need retrieved content R2 instead of the most up-to-date information R3. So this allows us to overlap the latency between retrieval and generation. And later on, we'll see techniques that can mitigate the staleness of this retrieved information. Now, the second technique here is that we want to adjust the retrieval paradigm of the original retro model a little bit, because the retro model basically forces the retrieval interval to be a fixed interval of every 64 tokens, which is also equal to the query window size. On the other hand, there are a couple of problems with this. First problem is that the retrieval latency may not be perfectly overlapped with this generation of 64 tokens. Sometimes retrieval can be longer, sometimes it can be shorter. So it's not easy to form a perfect pipeline. The second reason here is that we have some query staleness. So if we insist on a rather long iterative retrieval window of 64 tokens, then the retrieved information might be too stale to be useful. So here, what we do is that we actually allow flexible retrieval intervals. We allow this to be configured to, let's say, every 32 tokens, every 16 tokens, etc. So by having this flexibility, it's easier to overlap the latency between retrieval and generation. And also, if we use more frequent retrieval, then we can actually reduce the query staleness during the generation process. Now, another very interesting problem here is that, in fact, neither the latency of generation nor retrieval is a constant latency. So it's very tricky to overlap inference and retrieval latency. Now, let me give you one example. So here we show the generation latency. In this figure, the x-axis is the sequence length and the y-axis is the inference latency. And as you can see here, basically as the sequence length grows, we'll need to pay more latency to generate a single token. And the reason is pretty straightforward. It's because of the attention mechanism we have to pay. So every token we generate, we need to have more memory access to access the KV cache. Another interesting observation is that retrieval latency is also not a constant because there's always this fundamental trade-off between retrieval quality and retrieval latency in approximate nearest neighbor search or so-called vector search. So in this plot, you can see the x-axis means the search space in the database. Essentially, it means in this approximate nearest neighbor search process, how many database vectors are we going to scan before we return the query result? So as we increase the search space, you can see this orange line, which is the latency line, always increase linearly with the search space. And with respect to that, the search quality, which is the purple line here, often measured by recall, precision, etc., will also grow gradually before it eventually saturates at some point. So it turns out that the search place is actually a parameter we can tune for the retrieval process. And we can basically tune it to arbitrary trade-off between latency and generation quality. So overall, here we have both varying latency of inference and retrieval. So the question here becomes, how can we construct a perfect pipeline given all this latency are changing constantly? So the solution here is that we have this performance-driven retrieval system, which means that if we have a known retrieval interval, let's say we retrieve every 32 tokens, then at the time we generate the next generation window, let's say next 32 tokens, based on the existing sequence length and based on the underlying hardware print form, we can use a model to predict what is the expected generation latency. And based on this generation latency, if we want to perfectly overlap the generation and retrieval, then we can use another model to predict what is the maximum number of database vectors I can scan within this latency budget. And for this, we basically use a pretty simple linear model that is trained upon this database index and also based on the specific hardware platform. So given the latency budget, we can predict the maximum of database vectors we can scan in order to achieve the best retrieval quality. So in summary, the solution of PipeRAG targets a problem of iterative retrieval generation. And we have a huge system efficiency issue here because of the dependency between the retrieval and the generation process. So to solve this problem, we propose PipeRAG, which is a threefold solution that ranges from algorithms to systems. First, we have this data prefetching mechanism that allows usage of a stale query window and some staleness in the retrieved content. And the second solution here is that we allow flexible retrieval interval to reduce the query staleness because now we can increase the retrieval frequency. And finally, we use a performance model-driven retrieval system that can basically allow perfectly pipeline retrieval and generation process. Given a generation latency budget, I'm going to automatically maximize the retrieval quality based on this latency constraint. Now let's take a look at the evaluation part. So in terms of evaluation, we use a vector data set we constructed from the C4 data set. It's a pretty large data set containing more than 4 terabytes of vectors. And in terms of models, we use this retro checkpoint as indicated in this reference. In terms of hardware, we use an A100 GPU as well as a pretty powerful CPU server for the retrieval system. Now let's take a look at the end-to-end generation quality. So in this figure on the x-axis, we can see that we evaluated various sizes of these databases, small, medium, large, and y-axis is the perplexity, which basically represents the generation quality. And the lower the perplexity, the better the generation quality. We evaluated different RAG options. The blue one is the vanilla RAG, basically RAG with only one retrieval at the beginning. Green one is the retro solution, and the pink one is our PipeRAG solution. And as you can see here, PipeRAG not only achieved the same level of accuracy of retro, but actually slightly outperformed retro in terms of quality. So let's take a look at why this is. So this is essentially because retro can allow more flexible retrieval intervals. So even if you use somewhat staleness in the query, we can still increase the retrieval frequency to compensate this quality gap. So you can see in this figure, the x-axis shows the search space on the database. So the larger the search space, the more amount of database vectors I'm going to scan in this query. And y-axis shows the perplexity. And here we evaluate different options for PipeRAG of different retrieval intervals ranging from 8 tokens to 64 tokens. And for retro always use a fixed configuration of 64 tokens due to its design of its attention mechanism. And here we can see this gray line is the retro baseline. And as we increase the retrieval frequency of PipeRAG, let's say reducing the retrieval interval from 64 to 32 to 16 to 8, then we can improve the performance in terms improve the quality of the generation. So eventually, PipeRAG can achieve better generation quality over the retro baseline. Now let's move on to the quality aspect. So what about the performance? In this plot, we show the two-dimensional aspect. X-axis is perplexity, Y-axis shows the performance represented in latency, and both is lower is better. And here you can see that PipeRAG basically outperforms the retro model in all the cases by adjusting different setup of retrieval quality and retrieval interval, etc. So here, essentially, PipeRAG can outperform the baseline in terms of retro in both performance and quality simultaneously. Now, one thing you might wonder is that both retrieval and generation latency really depends on the underlying hardware platforms. So how would PipeRAG perform on future hardware? For example, if we invent a better accelerator for the models, and suddenly the inference is going to be 10 times faster, what will happen for the PipeRAG solution? And vice versa, what if we have a better retrieval system? So here we basically evaluated a simulated scenario where we imagine the retrieval or the inference is going to be running on a faster platform, let's say from 2 times all the way to 16 times faster, while the other component remains the same performance. And here we show you 4 figures showing different scenarios. On the top, you see 2 figures. Imagine we have an inference engine that is 4 times faster or 16 times faster. And the bottom 2 figures shows the scenario where we have faster retrieval engines. And across all scenarios, you can see that the PipeRAG solution, which is basically the green line here, outperforms this retro solutions in all the cases. So basically, regardless of the specific system performance of individual hardware, PipeRAG can achieve better generation quality and performance frontier. One thing I want to mention before I close this talk is that we did this work back in 2023. And back then, retro was the popular model for iterative retrieval, so we built on top of it. They were moving to a different era with different models, but we still face similar system efficiency problems. So one thing we use today is this large reasoning models, and still they use multi-hop retrieval style, but the style is a different in terms of its dynamic, because these large reasoning models can issue this retrieval at any given moment during the generation process. So it's not like retro where we have a fixed interval. We do a retrieval every 64 tokens. So how to solve latency overlapping in this very dynamic scenario definitely deserves future work. And also, now AI agents can invoke tools or even interact with each other. So when I invoke these tools, these agents basically pause and waits for the results to be returned. Although it's not retrieval, the system efficiency issue is actually very similar because the model will wait before it can do anything further. And this waiting process can sometimes see even undeterministic latency. So how can we improve systems for agents like this? It's also a very interesting question. And in conclusion, we address the system efficiency issue in RAG with iterative retrievals. We propose PipeRAG, which has the threefold solution from algorithms to systems. First, we allow data prefetching that allows some query stillness and retrieve content stillness in order to support the pipeline parallelism in between retrieval and generation. And second, we also allow flexible retrieval interval in order to reduce the query stillness. And finally, we propose this performance model-driven retrieval system that can automatically adjust the retrieval configuration based on the generation latency budget in order to form a perfect generation retrieval pipeline. And by combining all these solutions, PipeRAG achieves not only better latency, but also without any quality compromise. With this, I'm happy to conclude my talk here and also happy to take off your questions.